Alright, hey everyone, welcome back. It's been a while since I posted. This is for the Austin Great Wall Chinese School FMA class. I'll be reviewing over the Class 7 quiz and just explaining some of the things. This looks like I have a slideshow prepared. I don't have a slideshow prepared. This is just to keep everything, I guess, classic, I guess. Alright, so, these are all questions that were taken from the 2023 FMA exam. You can even see them all labeled here. First 7 questions are literally in verbatim, and then we have a few skips, but it's quite nice. So, let's start. A bead on a circular hoop with radius 2 meters travels counterclockwise for 10 seconds and completes 2.25 rotations, at which point it reaches the position shown. In the past 10 seconds, what were its average speed and direction of its average velocity? Alright, this is not too hard. Let's just switch over. I'm a bit rusty. So, we have a circle. We have a hoop. That's not a hoop. That's a hoop, but it's not circular. We have circle. Okay, so ending position. This is the ending position of the ball. This travels for 10 seconds around a hoop with radius of 2 meters. 2.25 rotations, right? And it asks us for average speed and average direction, and direction of average velocity, right? Let's first determine the direction. It's a lot easier. So let's first retrace our steps. We end in this position, right? So let's go to the beginning position. So 1 rotation, 2 rotations, and then a quarter of a rotation, right? So all the way up here, and this is our beginning position, right? Somewhere there. That means that our average direction, remember that these 2 rotations are going to cancel out the average direction, right? They're all going to be pointing, I guess, down because that's where it starts. But its average direction is basically canceled off. It's only the last stretch, remember, it's going counterclockwise, right? It's only this last stretch that's going to count or determine the direction of the average velocity, which means that the average velocity, if we just draw like arrows, this is going to be the direction. We know that the average is going to be somewhere in this direction. That already eliminates answer choices A, B, and C. So now we're just down to D and E, right? All right, so we know that the average, oh God, no, that's not what I wanted. Oh, wow, my handwriting sucks. So first of all, we know that the direction is in this direction now, right? Of its average velocity. Now we need to calculate the actual average speed. So how are we going to do that? We first need to know the circumference of the circle because we want to know the total distance traveled. We only need one equation here, which is V equals D over T, right? This is going to be our average speed throughout the entire event, I guess. But that means that we need to know the distance. We already know the time, so we just need to know the distance. Distances traveled, we know we have 2.25 rotations. We just need to know how long a rotation is. Circumference, we know, is going to be 2 pi r, which is equal to 2 times pi times another 2, which equals to 4 pi meters, right? That's the total circumference. We multiply our distance is equal to 2.25 times this 4 pi, which is going to be equal to 9 pi. Putting that back into this equation, that's going to give us our average speed is going to be equal to D over T, which is equal to 9 pi over 10 seconds, meters per second in this direction. And so that's going to give us answer choice E, 9 pi. All right, that's simple. Next question. Oh, no, what have I done? Let's see the slideshow, right? No, okay. Technical difficulties. Let's clicking on the wrong one. You can see that, right? Nice. Okay. So, next question. This is the second question. A mass on an ideal pendulum is released from rest at point 1. When it reaches point 2, which of the following shows the direction of its acceleration? And it gives us a few little arrows, which is kind of nice. This is quite simple. There's always going to be some kind of pendulum problem on an FMA exam. And it's just really nice to memorize what that's going to look like for velocity and acceleration. So I actually have a GIF pulled up here. I love this GIF. I want to pull this up. I pulled it up. Okay, so I love this GIF so much because it's so nice to memorize. I tell everyone to just memorize this, even for regular physics. So it's just nice to know like how the velocity moves, how it reaches its maximum, and it's also really key to know how like the acceleration moves. We can see like the vector kind of does this kind of motion, almost like a little fan or something. But yeah, this is really nice to know. And so judging by that, we can absolutely just like, if we want to, we can memorize this and be like, oh, okay, it's if we release it from rest here, it's gonna have something in the middle here. And so if we go back here, we'll know, okay, it's B. But if we actually want to do it with some more like actual physics or something, we can do this, right? I'm gonna move OBS aside. So we know that for vectors, right? Our acceleration vector, our total acceleration, is going to be equal to our centripetal acceleration plus our tangential acceleration. That's how we get the equation of this, where it's AC squared plus AT squared. This doesn't count a direction. It's just the magnitude. Right, that's the word. Yeah, the magnitude. But this is the actual vector equation, right? We have, what is this? Our pendulum starts at point 1. We're asking the acceleration at point 2, right? Wow, this is very well done. So we know that our centripetal acceleration is going to be pointing in this direction. Our tangential acceleration is going to be pointing in this direction. So our total acceleration is going to be somewhere in here, probably like here or something, right? And that means if we go back to our worksheet, that's going to give us answer choice B once again. And yeah, that's how you do it. It's just simple vector addition. Sorry. Next, a soccer ball is kicked up a hill with a flat top as shown. The ball bounces twice on the hill at the points shown, then lands on the top and begins rolling horizontally. Which of the following shows the vertical component of its velocity as a function of time? Vertical component, that's going to be important. Alright, what is this? So, we have a hill. We have another flat part. Our ball starts from here, bounces twice, and then lands here, right? At which point there's no longer a vertical component. We're looking for the vertical component of its velocity versus its time, right? And this is going to be important. So, first of all, let's just look back at our answer choices and use some process of elimination. A, B, and C are wrong. And I can almost prove that, right? At this point, there's going to be a negative vertical velocity at this point, right before it hits, right? And then after it hits, it's going to have an upwards, a positive vertical velocity, right? So we know that our graph, here's our graph, Vy over t, right? Our graph is going to start high, go down here, and there's going to be a discontinuity, right? So that eliminates A, B, and C. Now we're stuck with D and E. D, I'm pretty sure it's going to look something like this, where everything is equal until the last bump. And for E, we have one where it's slower and then goes up, and then it's even smaller, and then it goes up here and ends, right? Or something like that, right? Double check. Yeah, well, there. Nice. Okay, so, okay, this is simple. Vy is going to be lower once it bounces up. You see how it's higher up? That means that the vertical velocity is going to be slightly lower, right? Once we swap, it's almost like cutting it off halfway and then starting up again, right? And so that's going to give us, if we look back, that's going to give us option E, right? Okay, so number 4. A box of mass m is at the bottom of an inclined plane, my favorite, with with angle theta to the horizontal and height h. A person drags the box very slowly up the plane by applying a force parallel to the plane. The coefficient of kinetic friction between the box and the plane is mu k. When the box reaches the top of the plane, how much work has a person done? Alright, first of all, inclined plane. So we have this, and then we have this. I thought you were stuck there. Alright, so we have right angle, and this is an angle theta. We have a box here. We push it up a height h, and we're determining how much work is done. And we also have a frictional coefficient of mu k. Oh, wow, this is badly done. Mu k, right? All right, so we can use the equation work is equal to force times distance. I know you can do work energy theorem. That's absolutely a wonderful alternative where you can say this is equal to the change in kinetic energy and then do some actual like smart stuff where you have 1 over 2, well, like not that, but you have non-conservative stuff, right? Why can't I control Z? There we go. All right, but we're gonna stick with force times distance, right? So first, our distance. This distance can be calculated by h divided by sine theta. This distance, let's just call that d, equals d. If you think about it, that makes sense. SOHCAHTOA sine is equal to opposite over hypotenuse. That means that d sine theta is equal to d times opposite opposite over hypotenuse is equal to h, right? And then you just move stuff around, divide sine theta, and you get that, right? We don't need that anymore. So you get this. That's our distance. Second, we gotta find the force, right? So this is a great time to draw a free body diagram, and I'm gonna do this in a very bright, not too bright. I don't like colors. This nice gold, right? Free body diagram. Nah, that's not how you spell free body diagram. Free body diagram time, right? All right, free body diagram. Let's draw it for this box, right? This box, we have some kind of force pushing on it by the person. Force. We have a normal force. We have a gravitational force, Fg. And this is vertically downwards. And we have some kind of friction, right? Frictional force. All right. So I'm gonna keep this here for a moment. I'm gonna move this down. So our gravitational force can be split into two components, right? We know this. This can be split into. I'm not gonna change the color. We have this component and we have this component, right? So this is going to be g sine theta. This is going to be g cosine theta, or mg cosine theta and mg sine theta. So first of all, we know that we now have two forces that are pointing in the opposite direction of this force, right? One is the frictional force, and one is the gravitational force in this direction, right? And we can actually simplify this, right? Fg, let's just say down or something, right? This frictional force is going to be equal to mu times n, which is going to be equal to mu k mg cosine theta, right? And this down is going to be equal to mg sine of theta, right? All right, so we've gotten to this point. We know that our F is going to have to counter both of these, right? In order to push up. And so that means that we have force times distance. So mu k mg cosine theta plus mg sine theta times h sine theta is equal to the total work. This is our answer, hopefully, if I did everything right. And if we check back on our worksheet, we actually need to simplify this a little bit. I'm going to go back to my equation. Yeah, okay, this makes sense. They're just removing the divide by sine theta, right? Okay, so I'm going to pull this back up. I'm going to keep this zoomed in. I just don't know how to move this around. I'm just going to hide everything. We now have, let's just go to purple. We have, what is it? Mg sine theta plus mu k mg cosine theta. And all this is multiplied by h sine theta, which is equal to the work. We can bring this mg out, right? The h is already out and the sine is somehow put inside. So this is going to be equal to mgh. Sine theta divided by sine theta is 1 plus cosine theta divided by sine theta is equal to the cotangent theta, right? And this is multiplied by mu k, because you can't forget about that stuff. And if we go back, that is going to give us, I have cotangent, so that's going to be E. It's going to be E. All right, question 5. 2 blocks of mass m and a block of mass 3m are attached to a system of massless fixed pulleys and massless string as shown. Assume all systems are frictionless. What is the acceleration of each mass m? All right, this is a simple one. What does our diagram look like? Let's pull out the black. V. Of course it's slanted. We have 2 here, 1 pulley here, 1 pulley here. And then we have, what is this? It's something like that. Oh god, this is terrible. I'm gonna do this again. So we have this and this. We have pulley here, pulley here. We have here, we have here. We have this block of 3m mass, and we have 2 blocks each of mass m dangling like this. This looks weird. Wow, 2 pulleys. So scary. But if we rethink this, this is quite literally just a one pulley system where we have a mass of 2m on one side and a mass of 3m on the other, right? Because both of these are pulling up, right? Everything has to have the same acceleration. And if we remember anything about Atwood's machines, the equation that we're going to get for our acceleration of everything is going to be acceleration is equal to g big M plus little m divided by, that's not right. Big M minus little m divided by big M plus little m. And these are just fillers. We can replace these with the actual values, which is equal to g times 3m minus 2m. 3 minus 2 is 1, so that's going to be 1m divided by 3 plus 2 is 5m. Cross these out, and that gives us an acceleration of each of the masses of g divided by 5. Remember that the acceleration has to stay the same for the entire system, because this is a system acceleration. So that's going to give us g over 5 for each of the blocks. And that's going to give us answer choice B. Nice. Number 6, and there's the actual scene that I wanted. Number 6. I can't read. A ball at the end of the rope of length 0.5 meters is swung in a horizontal circle with a speed of 15 meters per second. The other end of the rope is fixed in place. What is the height difference between the ends of the rope? Alright, this is nice. So, what is this? We have a rope 0.5 meters long, and we have 15 meters per second spinning velocity, right? We can actually get the tangent of this. So let's draw a little diagram for this, right? We have a rope that looks like this right now, right? There's 2 forces acting on the ball. There's the centripetal force and the gravitational force. All right? And we can also use quite a bit of angle approximation for this, just because our final answers, if we look back, are in centimeters, even though we have a 500 centimeter long, 50 centimeter long rope. Our answers are like 1.1, 2.2, stuff like that. It's really small. So we can actually technically use some angle approximation. So we have something like this. We have an angle here. We have centripetal force, which is mv squared over r. I'm smart. That's right, yeah. And we have gravitational force, which is mg. So we can say that the tangent theta is going to be equal to our opposite over adjacent. Yeah, so mv squared over r. No. This is theta. I'm smart. I'm very awake right now. Control. No. For the key binds. Okay. So tangent theta is going to be equal to opposite mg over adjacent, which is mv squared divided by r. Nice. And since we are using angle approximation, this is going to be approximately equal to tangent to r theta. Please let me control. Oh, it's because I'm pressing on my graphics tablet. Okay, so this is going to be equal to. Let's actually use purple for this. This is going to be equal to. We can cross out both m's. R moves up, so this is gr over v squared. Isn't that so handy dandy convenient. That means that this distance, right? This distance is going to be equal to L sine theta. L being this hypotenuse, right? So our hypotenuse times opposite over hypotenuse, that's going to give us the opposite, which is how much this deviates by, right? So our hypotenuse is going to be L. That's going to be the length of the string, which we've already denoted here as R. So we can just say L is equal to R, and that means, I have the eraser on, our final length is going to be L sine theta, right, of how much it drops by, which is equal to L theta, or not equal to, approximately L theta, which equals G R squared over V squared, which is equal to 10 times 0.5 squared divided by 15 squared. I don't have my calculator here with me. I gotta plug that in. Calculator. No, you see my gaming addiction. Calculator, here. So we have, what is this? 10 times 0.25 divided by 15 squared. That's 25, right? 25, I'm sorry. Yeah, and so that's going to give us 0.01111. And since this is in meters, we can convert this to centimeters by just multiplying by 100, and that gives us around 1.1 centimeters. And if we go back to our slide, not our slideshow, our worksheet, that is going to give us it's A, 1.1. All right, number 7, 2 boxes are stacked side by side on top of a larger box as shown. All 3 boxes have mass m. The coefficient of static friction between the left box and the bottom box is mu s, and all other surfaces are frictionless. A rightward force F is applied to the bottom box. What is the minimum value of mu s so the upper boxes don't slide? It's quite an easy one. All right, so cursor please. Cursor please. All right, we have 3 boxes in total, right? Each has mass m. And we have this bottom one, right? So, m. There's a coefficient of static friction of mu s. Everything else is frictionless. And we have a force of F here, right? There's a questionable way of doing this. This is how I did it. We can treat these 2 boxes as one box with 2m for the time being, right? This box has a mass of 2m. We know that everything here has to have the same acceleration, an acceleration of F divided by 3m, right? We're split in 3 parts, so this top part has essentially a force moving in that direction of 2F over 3. 2 parts of all 3 boxes in order to accelerate these 2 masses at the same rate as the entire system, right? So all of this has to be applied, what am I trying to say? All of this has to be supplied by this leftmost box. So that means that our mu singular mg, because it's just this one box that has friction, is equal to 2f over 3, because there's 2 boxes out of the 3 that are moving basically on the same level, right? And so that means that our mu s is going to be equal to 2f over 3mg. This is a slightly different way of doing it, but if we look back, that's going to give us an answer choice of D. It's answer choice D. Nice. Okay, number 8. An archer takes aim at a target that is 100 meters away. Assuming she holds the bow at the same height as the center of the target and shoots an arrow with velocity v equals 100 meters per second, at what angle above the horizontal should she aim the bow so that the arrow hits the center of the target? I can speak today. Okay, so we have archer denoted by that. We have target also denoted by that. There's a distance of, that's a straight line, of 100 meters. And she shoots an arrow at some particular angle, theta, or something, I'm going to say theta, with a velocity of 100 meters per second, right? And this goes in like a projectile motion shape and lands in the center of the target. Right, okay, so this is quite simple if you remember the three equations, right? We have time, range, and height. And I can write them out here just as reference. So time is equal to 2v naught. I remember this actually. Do I remember this? I remember this, right? V naught squared sine theta over g, I think. Is that right? Maybe not. Oh, okay. Well, a bit late for that. Let me actually... Alright, technical difficulties time. I'm gonna do some background research. Where's my Quora? Where's my Quora? There's one picture that I love so much because it actually does its job really well. Oh my god, okay. Taking its sweet, sweet time. Oh, it might be here. Wonderful, it's not. There it is. Okay. Oh, I was not completely correct actually. So t is equal. Oh, this is really simple too. 2v over g. Remember that? Remember this? Probably because I didn't. 2v naught sine theta over g. Range is equal to v naught squared sine squared theta over 2g. And this is going by v squared over 2g. Finally, our height is going to go by some trigonometry based on time. And that's going to give us v naught squared sine 2 theta over g. Right, these are the three equations that you must know and that I must properly memorize after this. I don't have time to call. I should have turned on Do Not Disturb. Alright, so that means that our range is going to be equal to v naught squared sine squared theta over 2... No, sine 2 theta. Did I mess that up? Oh, I messed it up. Alright, this is sine 2 theta over g. I'm smart. Okay, I memorized them in the wrong order. Let's do this again. I'm having a great time. Time is equal to 2 v naught sine theta over g. Range is equal to height. No, let's do height next. Height is equal to v naught squared sine squared theta over 2g. This is the equation. I'm very rusty right now. And our range is going to be equal to v naught squared sine 2 theta. That's not clear. This is supposed to be an exponent. Theta. Something like that. Let's just keep it this way. Just remember it. Okay, this is a square. This theta is not part of the square. No. Okay. We have those. Now that that's cleared up, let's use the range, the correct range, which is equal to v naught, I wrote this just now, v naught squared sine 2 theta over g, which is going to be equal to, let's just plug stuff in. Our range is equal to 100. Our velocity is 100 squared. Sine 2 theta divided by g, which is 10. Cancel these off. Cancel this. Move this to the other side, and now we have sine 2 theta is equal to 1 over 10. Let's pan this down. That means that sine, not sine, 2 theta is going to be equal to arc sine, right? Arc sine 1 over 10. And then we divide 2 on both sides. these cancel out, and we get theta equals arc sine of 1 over 10 divided by 2. Finally. I did not even have the C note. I'm so disappointed in myself. I'm not even going to try again. Here's where we are. I had the technical difficulties page. I wrote so much. Okay. Oh, I'm not awake enough. Okay, so time, again, is equal to 2 V naught sine theta over G. I'm blaming my dad for the call. Height is equal to V naught squared sine squared theta over 2G. Over 2G. Over 2G? Over 2G. That revealed my DMs. Range is going to be equal to V naught squared sine 2 theta over G. Okay. That took too long. I am so sorry. But, finally, back to the point. This is our answer. Arc sine 1 over 10 divided by 2. That's theta. Why did I minimize? That gives us an answer of D. D, yeah. 1 over 10. Arc sine 1 over 10 divided by 2. I am so sorry for putting you through that. What is that, like 5 minutes? 6 minutes of you just looking at a blank screen? I'm so sorry. Anyways, number 9. A projectile is thrown from a horizontal surface and reaches a maximum height h and also lands a distance h from the launch point. Neglecting air resistance, what is the maximum height of for a projectile thrown directly upward with the same initial speed? This is an interesting question. It takes a little twist on the range equation, right? So, first of all, we know that the range must equal to... Oh, shoot. I should actually, write this out, right? So, originally, when we threw it at an angle with a certain velocity, it goes to a maximum height of h, and it also moves a distance of h, which means that our range and our height are going to be equal. So, range equals height, which means that... let's change this to purple. V naught squared sine 2 theta over G is equal to V naught squared sine squared theta over 2G. Alright, that's quite simple. Let's start eliminating stuff. Velocity, gravity. And now we get to a point where we have sine 2 theta is equal to sine squared theta over 2. Now this is where we get that trigonometry back again, and that's the edge of the paper. Sine 2 theta, I'm going to do this in gold, sine, my handwriting's beautiful today, sine 2 theta is equal to 2 cosine theta sine theta, right? That means that we can say that this is 2 cosine theta sine theta is equal to sine squared theta divided by 2. Let's move this over. Now we have 4. Let's cross this out, remove the square, and now we have sine theta equals 4 cosine theta. Now here, there's a smart way of doing it, and there's an absolutely stupid way of doing it, and I'm going to teach you the stupid way, because I did it. And so, there's, it uses some alternative thinking, right? We know SOHCAHTOA, right? I'm going to write this in gold because apparently I'm writing concepts in gold. SOHCAHTOA. SOHCAHTOA. Right? We know that our sine is going to be equal to our opposite divided by our hypotenuse, and our cosine is going to be equal to our adjacent divided by our hypotenuse, right? Since we have this equation, we can say that our opposite divided by our hypotenuse is going to be equal to 4 times our adjacent divided by our hypotenuse. We can now cross out the hypotenuse on both sides, and our opposite is now equal to 4 times our adjacent. What does that mean? That means if we draw a triangle, we have an angle here, and we know that our adjacent is going to be that, and our opposite is 4 times our adjacent. That means, by Pythagorean or Pythagorean theorem, this side, this hypotenuse, c squared is equal to a squared plus b squared. C is going to be equal to the square root of a squared plus b squared, or 1 squared plus 4 squared, which is equal to the square root of 17. What does that mean? Alright, I'll show you what that means. If I can figure it out. Oh, I'm running out of space. Let's... Oh, I forgot my... Oh, that actually helped a lot. Let's shrink that down. Oh, no. There we go. Let's move this up. We're here, right? Alright. So, now we're on the final stretch. Height, remember from before, is equal to v squared over 2g, right? If we plug that in to what we originally had for our velocity, that means that our height is equal to our... What is it? What did I do? The original height, or height prime, in this case, is going to be equal to our original height divided by sine squared theta, right? And that, my friends, is how we get that our h prime is equal to h divided by, remember how sine is going to be our opposite over our hypotenuse, which means that this is going to be opposite of 4 divided by hypotenuse, which is 17, square root of 17 squared, which is equal to 17 over 16h. And if we go back to our worksheet, that is going to give us the wonderful answer of A. That's a satisfying problem to get rid of. Alright, number 10. I'm so sorry for taking so much time. A block of mass M is initially held in place by 2 massless strings as shown. The tension in the diagonal string is T1. Next, the horizontal string is cut, and immediately afterward, the tension in the diagonal string is T2. Which of the following is true? Alright. Let's erase this. Okay, give me a moment. I need some... Just not mess up technical difficulties this time. Can I just delete this? I can! Oh, I don't know how to use Krita anymore. So, we have V. We have V again. I'm just yelling out my key buttons. We have V for a 4th time. And we have a box here, right? Before the string is cut, this string is at T1. T1, if we draw a free body diagram, we can say that T1 is equal to, T1 cosine theta is going to be equal to mg, right? That means that the vertical component of the tension is equal to the gravitational force. Or not the horizontal, the vertical component. Vertical component is equal to the gravitational, right? We can also say that T1 sine theta is equal to the tension in this string, but that doesn't really matter. All we can say is that T1 is equal to mg divided by cosine of theta. Since cosine of theta is less than 1, that means that T1 is greater than mg. Right? Wait, what am I trying to say? Am I trying to say the right thing? I'm saying the right thing. Yeah, I'm sorry. Yeah, so T1 is going to be greater than mg. That's going to be an established fact, right? So let's remove all this. And now we know that T1, let's label this in gold, T1 is greater than mg. Next, we're going to cut this string. We're going to say goodbye, you're gone, and now the string is cut, right? In this moment, we have two forces that are going to have a general centripetal component. All right, so if we were to change this, our net force is going to be a centripetal force, right? So we have T2 plus mg cosine theta, or what? Okay, everything's fine. Theta, or should it be minus? Probably minus mg cosine theta is going to be equal to our centripetal force, because in this moment our pendulum now starts experiencing centripetal force, right? It's going to start swinging and having this component, right? So remember mg cosine theta. So here, right, we're going on this axis here. We have T2 minus this is equal to our centripetal force. Centripetal force is equal to mv squared over r, but since this is immediately after the string is cut, v is equal to 0, so that means that our centripetal force is still 0, right? That means that our T2 is equal to mg cosine of theta. Remember how I said cosine of theta is less than 1? That means that T2 is less than cosine of theta. Not less than cosine theta, what am I saying? Is less than mg. Alright, so let's mark this in gold again. T2 is less than mg. Why are we saying mg? Because all the answer choices go by that. We were having a comparison. And that means, going by that logic, that we get the answer choice of B, where T2 is less than mg, which is less than T1. Great. Now on to the final and hardest problem. A skier slides from rest along a frictionless slope with incline angle theta equals 30 degrees for 150 meters, then smoothly transitions into a horizontal jumping ramp of height HR is equal to 5 meters. Neglecting air resistance after the skier leaves the ramp, about how far will they travel horizontally before landing? Oh, I have my scene wrong. To be completely honest here, for the actual competition, I may or may not have guessed the right answer from deductive reasoning. But let's do this the accurate way, right? V first. Close enough. So, first, our skier skis down 150 meters, right? Then they transition onto this ramp with a height of 5 meters. Do some kind of jump and land some horizontal distance away, right? Okay, this is a fun problem. Very fun. Let's first start off by making this much smaller because we're gonna need that room. First, I need to look at my notes for this. All right, let's first flip the axis, right? We can do this because we can. I don't have an explanation for that. That way we can have projectile motion math like this, where we can measure our de facto gravitational force and kind of adjust everything on a different axis. And if you're smart enough, you'll realize that I aligned this axis onto this slope, right? So this slope is now on this axis, right? Nice. So, starting from there, let's first find out the initial height that it departs from. This h, let's just call this h instead of something weird, is going to be equal to our hr cosine of theta, right? Okay, that's the first point. Second point, once our object leaves, it has an initial vertical component of v naught sine theta, right? This is the v naught y, I guess, right? And we have a gravitational component, a downward acceleration, let's just say this is a, equal to g cosine of theta, right? And this is because g is pointing in this direction currently. The actual gravity is pointing in this direction, but we're currently measuring it as if it's like this, right? So this is g cosine theta, as with every single inclined plane problem. Alright, so now we have the basic components mapped. What are we supposed to do from here? Remember the kinematic equation of h equals vt plus 1 over 2 at squared, right? Alright, let's work off of this. Our initial height, or actually the height difference, is going to be the negative of this, right? Because we start from here and we go below that. So that means that we have negative hr cosine of theta is equal to v naught sine theta t plus, or minus actually, because we have a negative acceleration, right? Minus 1 over 2 g cosine theta t squared. And this is why I said I needed more space. Alright, this is great. This is nice. let's not do that. Where did my... Oh, I forgot all my keybinds. Oh, there we go. Nope, I remember them. All right. So, let's select this. I think it's this key. Let's move this out of the way. That's not what I wanted. Shrink this down. Now we have a second part of the problem done. Right? How nice. Moving on, let's first determine what V0 is, just to simplify things a little bit more. We can actually use both energy and dynamics. I'm going to use kinematics for some reason, where we can say that V is equal to the square root of 2AD. Remember this? Please remember it. You remember it. Okay. AD. This is going to be equal to the square root. We know that the acceleration is going to be that, right? It's that component, which is g sine of theta. So that means that we have 2g sine theta times d. D is going to be equal to 150. We'll remember that for now, I guess. V0, right? Okay. So let's also add some more stuff in. Cosine theta is equal to the square root of 3 over 2. Sine theta is equal to 1 over 2. This is basic trigonometry. Remember the unit circle, kids. It actually helps a lot. Okay, that means that if we start from here, now we have negative HR times square root of 3 over 2 is equal to this 2g sine theta. Sine theta is going to be 1 over 2, so these cancel off. So we can say this is GD divided by 2 times t. So we can just write GD divided by 2 times t minus cosine theta is square root of 3 over 2, which means that this is now g square root of 3 over 4 t squared. Let's rearrange stuff. Let's move all of this to this side. So g times 3 over 4 t squared minus square root of gd over 2t minus hr square root of 3 over 2 is equal to 0. Isn't that so fun? Oh, why do I have something wrong? I don't think I do, but this does not match my notes currently, but I think I wrote my notes wrong. I'm just going to pretend everything is fine, right? As we all do. Yeah, okay, everything's fine. Now we're at a different stage. I'm going to move this down and just like pretend the other stuff doesn't exist for a moment, because now we're in the realm of quadratics. Remember the catchy song that someone else made a while back for memorizing the quadratic formula? We're going to use that. So t is going to be equal to negative b plus or minus the square root of b squared minus 4ac. This is a square root, not an integral, over 2a. Haha, so funny. Anyways, let's actually start plugging stuff in, right? We have a positive a now. That makes things easier. Everything's on one side. This is equal to 0. That means that t equals square root of gd over 2 plus, we're not going to do the minus because that's going to give us the negative time, square root of b squared, so gd over 4 minus 4 times g times square root of 3 over 4 times this negative hr square root of 3 over 2. All of this under a radical, under a radical, over 2 times g square root of 3 over 4. All right, this is equal to square root of gd over 2 plus the square root of gd over 4 minus g plus, because these cancel off, g times hr times 3 divided by 2. I think that's correct. It's very hard to read my notes. All of this over g times square root of 3 over 2. Let's try simplifying stuff now. This over 2 we can actually eliminate from all of this, right? Because all this has some kind of thing that emulates that, right? So we also can eliminate a square root of g. So what we can do is multiply by square root of g divided by 2, right? On both the top and the bottom, I think. Am I doing this right? I'm doing this right. No, this is going to be 2 over square root of g. I think. Yeah, that's correct. Okay, let's actually keep that. That makes things really convenient. Which is equal to, oh, this is where things get hard. Square root of d, right? Square root of d plus the square root of this 2 cancels, right? This square root of g cancels. D plus 2. This is square root of 4. So this is now 3 times 2, 6 times hr, because g gets canceled. Divided by, oh, I'm exhausted. We eliminate the 2. We eliminate the square root of g. So now we have square root of 3 times g, with g under the radical. Okay, that is our time. That's all we can simplify by up to this point. I have more space to work with. Yes, I do. We've made a tremendous milestone, and it's only been like 70 minutes. Alright. Next, we know that our x is equal to vt, which is equal to the square root of gd times t. This is equal to, let's start plugging in stuff. This is equal to square root of 10 times 150, that's 1,500, times the square root of 150 plus the square root of 150 plus, what is that, 30, divided by the square root of 30. Okay, let's see if my calculator wants to cooperate. This is a hard one to deal with. Let's do this. Square root. No, that's not what I wanted. 150 square root. No, I know how to use my calculator. 150 square root. 180 square root. Actually, you know what? How do I do this? No, I don't know how to do this. I want to use a regular calculator. I don't have a regular calculator on hand. Square root of 150 plus square root of 180 divided by square root of 30, right? Is that what we were at? Times square root of 1,500. That gives us 181.47 meters, which is closest to answer choice C. There we go. There's your answer. Holy. Okay. Let's actually go back to the scene so I can feel accomplished. Which means this x is equal to 181.47 meters, which is answer choice C. Thank you so much for tuning in. I'm so sorry for making this so long. This is 53 minutes. It's probably going to be 54 once I end this off. Thank you so much for listening. Have a good day, or a good night, or a good weekend. I have no idea. I'm tired.